Yeah. I think I've already said this, but I'll repeat that I will put my lecture notes. I'll send them to you.
Okay.
So I'll send Shivaguru my lecture notes, and also I'll prepare a list of references for the various topics that were mentioned in the course. And if any of you also have additional resources to suggest or anything that came up, please just send them to me so that we can have it all in one place. So last time, so where did we kind of have discussed 3 different examples where this appeared, and I wanted to make this contrast about the contrast between the first example that we saw and then the examples coming from symplectic geometry. And the contrast was that in the first case, we were producing these families of disks that shrink to a point. And so that prevented the underlying hypersurface from being holomorphically convex. Whereas in the latter case, we were dealing with totally real objects where these shrinking disks cannot occur. In fact, I had mentioned that you just cannot have small disks. So I wanted to actually substantiate that statement. So I usually like to start with some sort of a proof that everybody can follow along with. So last time, we had made this definition just towards the end. So K in Cn is compact. And we said that the polynomially, or rather, I'm not so much interested in the hull, but let me say the following. So K is said to be polynomially convex if for every z not in K, so every z in Cn which is not in K, I can find a polynomial P on Cn such that when I evaluate this polynomial at z in absolute value of, and you'll also notice that I tend to switch between z and z. This is just a consequence of having taught in various places, but okay, so what I need to show is that I need to produce this polynomial P which does this. Okay, and the polynomial depends on this choice of point. And something I should mention is that I don't really need to choose a polynomial. I can just choose an entire function P, and then I can just do an approximation. So entire functions using power series expansions can be approximated, at least on compact sets, by polynomials. So I can in fact produce an entire function. And the reason why we did this, so remarks, if K is polynomially convex, then any attached holomorphic disk must sit entirely. So this is how it is related to the topic that we are interested in. And I only verbally said this. I didn't quite tell you, I didn't write this down, but one of the main significance, I mean, there are many reasons now why people study polynomial convexity, but one of the first reasons why this notion came up was to understand the following phenomenon. So if K is polynomially convex, then any function that is holomorphic on some neighborhood of K can be uniformly approximated. So this is a very strong form of approximation. Can be uniformly approximated on K by polynomials, holomorphic polynomials restricted to K. Okay, so this is your version of Runge approximation theorem in higher dimensions. So polynomial convexity gives you a sufficient condition to get Runge's approximation theorem. So that is the significance of this notion. And what we want to show, what I will show is that if your underlying set is a totally real submanifold, then we have local polynomial convexity. So let me write down the precise statement, and then we'll just go ahead and prove it. Okay, so throughout this lecture, N is always going to denote a smooth, compact. For the following result, compactness is not so important, but totally real manifold of real dimension. I'll always work with maximally totally real submanifold. I should say that if the dimension is less than n, then locally you can always view it as sitting inside a maximally totally real submanifold. So sometimes when you prove things for something like this, you can reduce things for lower dimensional totally real submanifolds, but that will not be of concern to us. Okay, and so the theorem we had stated last time. So let me write down the precise version. So given P such an n, there always exists a neighborhood U of P in Cn such that when I intersect U with M and I take the closure to make a compact set out of this, a bounded neighborhood. I don't have to say that because M is compact, but in any case, such that this is polynomial. So in particular, there is no holomorphic disk attached to M whose boundary lies entirely inside this neighborhood capital U. Okay. So just to have a picture over here, I have my capital M, and all I'm saying is that if you give me any point over here, then I can find a small enough neighborhood U so that this part of this piece, compact piece, this itself is polynomially convex, and so I cannot have a disk attached like this whose boundary is somehow entirely. Okay, so the disk has to be large in some sense. All right. So this is a local statement, so let me first, since the statement is local, polynomial convexity. So something to be careful about, polynomial convexity in general is not invariant under biholomorphic transformations because it's a statement that involves algebraic objects. Okay, so it's not in general invariant under biholomorphic. In fact, there are examples where you have something polynomially convex and a biholomorphic image of that is not polynomially convex. But what I want to do is I want to use normal coordinates, which I can attain by just a C affine transformation. So polynomial convexity is definitely invariant. I mean, it's basically invariant under automorphisms of Cn. Just like the way I've replaced polynomials by entire, I cannot say that it's invariant under biholomorphisms that live on a neighborhood of your compact set. But if the biholomorphism is coming from an automorphism of Cn, I'm fine. So it is in particular invariant under C affine transformations. So because of these two facts, I may assume that M is of the following form. So we discussed this last time. Even though I'm writing M globally like this, what I really mean is that in a neighborhood, I can write it as the graph. So I have these imaginary coordinates, and I'm really writing it as a graph on the real graph of smooth functions. Okay, and this is a consequence of one of the exercises that I gave you last time. So here, where P, whose components are P1 to Pn, is smooth, T infinity smooth, phi of 0 is equal to T phi of 0. Okay, and let me also introduce some notation over here. So, I use B N, forget this bold, so I use B and R to denote the open ball of radius R centered at the origin in Rn, and so closure will just be the closure of that, and so let MR denote the intersection of M with the tube over. I'll draw a picture. I'm taking the tube over this ball. And so all I'm doing is, this is what my M looks like. This is Rn. This is Rn. And this graph is n-dimensional. Okay, so please don't be misled. Only in n equal to 1 case you get these two regions inside and outside. But this is really a real n-dimensional object sitting inside Cn, sitting inside R2n. And all I'm doing is I'm cutting it off, taking a cube like this. Okay, so this object over here, this is your I'm just taking this tube and I'm focusing on this little piece. In any case, I need to take R small enough so that my M really does look like this above BNR, right? I mean, this is not really a global picture, it's already a local statement. And what I'll do is I will further, so let R0 be small enough. So because d of 0 is 0, I can assume a Lipschitz condition. I take R0 small enough so that when I look at norm of Px minus Px prime, this is at most half of norm of x minus x prime whenever x and x prime are coming from the closure of ball of radius R0. Okay, so that is the condition that I will use to establish what is my goal. My goal is to show that MR0. So this is potentially a smaller disk here, and the region of M above that is polynomially convex. That's what I want to show. And so what I will do is, so now you can think of this as P and R0, and I'll take points outside this, and I will produce polynomials, or I'll produce entire functions that exceed, that satisfy somehow this condition. It's a fairly simple proof, but it's nice to do some proofs so that you know that this is not all something that you have to take my word for. So first I'll start with the Z0, which lies, so case 1, I let Z0 lie in this tube minus this piece, which I'm trying to do. Okay, so I can write Z0 as X0 plus I Y0. These are all n tuples of real numbers. I'm just using this notation. So I've taken Z0 over here, and I'm going to give you a polynomial P of Z, be the following polynomial. I'm going to take summation Zj minus, I'll use the real part of this. What I'll do is I'll sort of project this down and see the piece, I'll see the point which is on the graph. Okay, so I'm going to take x0j plus I times Pj of x0. So Zj minus this, sorry, too many brackets. So this is a polynomial clearly in Z, and this is a global polynomial. And what I'll do is I'll try to compute it at Z0, and then I'll try to see what its value is on the set itself. Okay, so the set that we are trying to show is polynomially convex is this piece here. This is what we are trying to show is polynomially. Okay, so now if I plug in Z0 itself, so remember Z0 is x0 plus I y0. So the x0 and x0j are going to cancel, and all you're going to get is summation I times y0j minus pj x0 whole square. The inside piece is going to be positive, and I square is going to give you something negative over here. So this is going to be strictly negative. So at Z0, P is strictly negative. And let's try to also please interrupt me if computation is not clear. And now let C of the form x plus I px be actually in MR0. Then when I look at P of Z, and I'm only going to look at the real part of this, what do I get? So remember, my polynomial is of the form a minus p the whole square. So when I take real part, So if I have z, how do I say this? So, or rather, if I have z square, then the real part is just real part of z square minus imaginary part of z square, right? So the real part of this is going to be real part of this complex number minus the imaginary part, which is pj of x minus pj of x naught full square. J from. Now, what can I say about this? So I have this condition star, right? So because of this Lipschitz condition, this is at most a quarter of these things over here. When I split the, so what you get is this is greater than or equal to 3, 4 x, something like this, which is okay. So what have I done? I have produced a polynomial that is negative. It's real valued and negative at z naught, and its real part is non-negative on the set that we care about. Am I done? Like, does that work? I mean, what did I want? I wanted to produce a polynomial so that p at z naught is greater than this, right? What's the one trick that we all know how to apply when we write a qualifying exam in complex analysis? Exactly. So remember that I said that you don't actually have to work with polynomials, you can work with entire functions. So if I notice this, I basically want to make this term dominant. It's already real valued. So let f of z be, and we just have to do this carefully, e to the minus e of z. Because then you can see that when you take absolute value of f of z naught, you will get something which is greater than e, and when you take absolute value of f of z coming from mr naught, then you will get something less than e, and so you will get your required check. Then f of z naught is strictly larger than f is entire. So this at least tells you, so z naught is not in the hull of. We are not quite done because I really need to check that any point which is not in this set is not in the hull. I took my xenon to be from this tube. If I take xenon to be outside this tube, I still need to check something, but I leave that as an exercise. So check if xenon is not from this tube. Xenon is also not in the hull. And again, you can do this directly by hand. I mean, of course, once you know enough about polynomial convexity, you can use all sorts of results to prove this. But sort of the purpose of this proof was to tell you that at least some things can be proved from definition in sort of elementary fashion, in an elementary fashion. Okay, so that gets questions.
Is the Levy polynomial? The second, the order 2 part of the Taylor expansion, because
Levy polynomial of what?
Of, I guess if you wrote down that defining equation. It's not quite.
No, this is an end, not really. I wouldn't quite call it that.
High potential.
Yeah. Yeah, I mean, I have some of these things, they really like very no logic to them at the end of the day.
It just works.
Yeah, it works. And that's the frustrating part about some of these proofs, that you really have to cook up. Sushil would be very familiar with this. You really have to cook up like clever polynomials, and sometimes it's hard to explain.
Because it's actually some sort of approximation.
Yeah, so I wanted to actually make a remark about this, because this is also going to feed into this statement that, you know, why care about totally real So remarks. So this is what Sushil is saying over here, a little bit about how this is typically proved. So what we said is polynomial convexity is in sufficient condition to guarantee that holomorphic functions can be approximated by polynomials. If continuous functions on K can be approximated by polynomials. So I'm not going to write down. So let's this algebra over here is the space of C-valued continuous functions that are uniformly approximable by polynomials on K. So what we are doing is you just take polynomials, restrict them to K, and look at the closure of that space in the sup norm. Whatever you get, I'll call that Pk. And so if you know that every continuous function can be Pk always sits inside Ck. But if it is equal, if every continuous function on K can be uniformly approximated by Pk, then K being polynomially convex is a necessary condition for that. And typically what people do is they directly prove that locally you can always find a small ball where Pk is equal to Ck on a totally real manifold, which will imply polynomial convexity. And why should this statement not be that surprising? So remember that at the end of the day, our model for a totally real manifold is really a piece of Rn, and then you have the Weierstrass approximation here, right? So if locally my totally real manifold looks like Rn and Cn, then my Weierstrass approximation theorem already tells me that continuous functions should be approximable by polynomials. You will get polynomials in x1 to xn, but then you can just plug in, so those are restrictions of holomorphic polynomials. So this part is not surprising, and then this result, which by the way itself is not, there's something to prove over here. This is kind of a deeper result, and that gives you polynomial convexity directly. This proof is direct, but it proves something weaker. Okay, it only proves polynomial convexity. It doesn't actually prove this additional statement. Something stronger is true actually. But at least it serves my purpose, which is to tell you that you don't have these small disks. Other questions? Okay. So, yes.
Follow along the same lines. So, why does this work? Or where else would we expect this kind of trick to work?
This particular trick, in the sense that you need.
Speaking of this polynomial using the defining function essentially.
Yeah, so in general, if you're like the graph of a Lipschitz function,
right?
I guess, I mean, that's what I'm using over here.
Right.
So there are all these results where you can establish polynomial convexity of graphs. The problem is, as soon as you have a complex direction in there, this could become a problem. So I don't know how much you can generalize this particular technique. But there are all sorts of results where people take specific graphs,
right,
and then they give some conditions on when those are polynomially convex. So I suppose you typically cook up something like this using the graphing function. Sorry? To try sort of the first thing quadratic, and then yeah, I don't know any good reason why this quadratic. I mean, in some sense, you are looking at the distance from the graph, right? It's some complex version of that. So I think that's what it's going for. Okay, so let's. I'm going to state 4 theorems that are going to summarize sort of the status of analytic disks attached to totally real manifolds, and the same thing holds. Capital N is always a smooth, compact totally real submanifold of dimension things. So the first result is a regularity result. And it goes back to TIFR from 83. I will will sketch a proof, and the proof that I'm going to sketch is actually from a paper by Bell and Lamport. So after Chirpa, Rose also kind of improved the technique a little bit. Chirpa's result is much more general. He's interested in analytic varieties that are attached to various sets. We are looking at a very simple analytic variety, which is just a disk. Right? So what is the result over here? I'm not proving the most general statement. So suppose F is continuous, the closure, it is Cn value, and it is holomorphic in the interior, and the boundary goes and lies in this smooth totally real submanifold, then in fact F extends smoothly to the closeness. Okay, so if you already have a disk that is continuous up to the boundary, then actually you have C infinity smoothness. So this is an sort of a manifestation of what is often referred to as elliptic regularity. So when you have elliptic equations, you kind of first can gain some regularity of the solution, and you can do what is known as elliptic bootstrapping to sort of push it up. If the data is smooth, you actually get smooth solution. But I'm going to sort of directly, I'm going to sketch whenever I get, I mean, I don't know if this will happen today, but when I sketch a proof of this, we sort of use complex analytic methods. So it may not give you a lot of insight into this general technique over here. By the way, if you're interested in complex analysis, I would highly recommend that if you get a chance, you should do a course in elliptic. I don't know if people at CAM people offer an elliptic EE course. Or there's this book by Gilbert and Tubinger. That's a really good book. I think you should have a pretty good knowledge of the kind of methods. Not all of them apply because a lot of those results assume what is known as uniform ellipticity, which a lot of times we will not have in our situation. Nevertheless, it kind of gives you a sense of what kind of results to expect. Okay, so that's something we'll talk about. But before that, the result that this is A, result A. Result B is a non-existent result. So this is coming right, think of this as coming right after Romov's result about disks attached to submanifolds. So this is due to Alexander, who he basically inspected Romov's proof and tried to repeat that for totally real manifolds. So so we are going to discuss this example. There is a totally real torus in C2 that has no analytic disk attached to it. When I say no analytic disk, I mean no non-trivial analytic disk attached. We will discuss this example. It's actually not that hard to write. Result C. So before I can state it, I need a definition. So definition. So what Alexander was able to show, so he tried to mimic Gromov's proof. He tried to simplify it a little bit in the totally real case, and he was able to show something. So here's a definition. Nearly smooth analytic disk of class CK, okay, I guess attached to M is a bounded holomorphic map basically these are disks which are attached everywhere except at one point of the boundary. Okay, so they're nearly attached, so a nearly smooth analytic disk of class CK attached to M, and these I'm going to call, I mean in the literature these are sometimes known as A disks, CKA disks, so A for Alexander, is a bounded holomorphic function F from the disk to Cn such that F extends as a CK smooth function to minus a point on the boundary. And if I look at where this boundary minus the point goes, it goes in lies. Okay, so what we are doing is we are allowing, so the attachment is not complete. There's one point that you cannot track, but the rest of it gets attached to the manifold in question. And I'll just use a disk to mean a C infinity smooth. A disk. Okay, so I'm not going to worry about lower regularity, and this is partly because of Chirka. By the way, Chirka's result is really local. Okay, so it's not like the full, I mean, wherever you have continuous attachment of the disk in a small neighborhood of the point, you will immediately get C infinity smoothness. Okay, so I'm not going to worry too much about whether this extends continuously or CK smoothly. For me, because the underlying manifold is always smooth, I will immediately get C infinity smoothness of the map up to that point. So for me, A disk will just be C infinity smooth. C infinity smooth up to B closure minus this mystery point that we cannot track. And to go from Alexander's proof or Alexander's theorem to Gromov's theorem, which Alexander does do in his paper, you basically just need to show that you also get attachment at P. If you are Lagrangian, in addition, you can extend the map to P as well, so you get fully attached disks. So I haven't quite stated. So this is just a definition. And what is, so theorem A was, what is theorem A? Oh, yeah. So regularity, non-existence. So we get some sort of relaxed existence. It's geometry. So it is a proof I will do. I will not do the PD style proof. I mean, so there's always a PPD. You always have to solve the D-bar equation, right? In the end, to produce a holomorphic function, you always have to solve D-bar, but they will be, so we'll use the Schwartz reflection principle. Okay, so I will sketch the main ideas over here because I think all of you will be able to appreciate that. So there is, the thing is that there will be a PD that we have to solve, but we'll be able to use the Cauchy transform to actually write down the solution. So it's going to be rather straightforward. And we are not going to do this, what I mentioned, which is called bootstrapping, for which you need these inequalities. Like you need to be able to relate the norm of the solution to the norm of the data. That approach is also there, but I'll sort of do the more geometric. So this paper, this Bell-Lampert paper, actually is about the Schwartz reflection principle. And they are interested in many things. They're also interested in attaching things to Levy-flat hypersurfaces. So the same paper also has techniques of, you have maps of this into, I think, I don't remember the precise result, but the same paper also contains results about that. So, yeah, so I don't think that's true if you have complex directions.
So everything is listening inside real.
No, but how do you have a, what do you mean? Oh, you mean
The boundary of the manifold is like kind of
this M, capital M? You want to increase the dimension?
Replaced by let's say bond.
Oh, this guy over here. Oh, this guy over here. Hang on. So let me understand what you're trying to do. You want to take so let's say you just want to take a 2 ball.
Yeah, 2 bond.
Yeah, I mean, let's say even locally. Let's not worry about globally. So I'm not so sure because so what you're trying to do is, okay, you're trying to attach a piece of the ball to, let's say, even RL. Is that even holomorphically possible?
I think if you have to.
Because it's going to have to try and push the complex direction.
Okay, where will the
complex direction
Okay.
go?
Yeah. Ball is like dimension A, then this dimension of the ball is 3.
Yeah, yeah, sure. B2. Let's take us two ball and let's say R3.
So we do already have complex structure.
So there's already these complex tangential. I mean, yeah. Yeah. I mean, at least for the Schwartz reflection kind of thing. So here it's not even clear to me how you're going to get a non-trivial holomorphic. So what you want is forget the rest of the ball, right? Just a piece of it. You want a holomorphic map, right? Which is taking the boundary to Rn.
Probably that's what I wanted. The difference real boundaries.
Yeah. So I think if a boundary is totally real, you can probably limit this proof.
So the problem is you can do S1 for S1, but then that's useless because there's no ETA, right? You cannot extend anything. Right? It's not the boundary of some nice. The reason this works is because.
So the thing is, how do you create something which has totally real boundary? Because the dimensions, so you're forced to work with planar objects. That's the problem. There is no automatically. Yeah, I mean, one should immediately be able to come up with a proof over here that you cannot have something non-trivial. Some maps.
It's clear, right? Because then you have it shouldn't work.
But I think you just cannot have a non-trivial map in the first place.
Exactly.
That's the concern. I mean, so trivially, yes, because your maps are trivial.
Yeah, so here, people have complex relation. So the holomorphic map, then they can go to complex.
Exactly, that is the intuition. One has to formally write this down, but I think this map is trivial.
Actually, it's not possible, but there might be many more there are complex directions.
Yeah. Then the regularity statement, I don't know if the same technique will work. You'll have to do something else. But I mean, for those of you who work with all these metric geometry kind of statements, you guys know how to do this for. I mean, if I look at this result in C, then you are truly working with domains. You're taking disk to a boundary of a domain. So there you can use whatever techniques you have to extend proper holomorphic maps. But then as you go in higher dimensions, that technique doesn't work. So for low 4 dimensions, so I guess we can put this down as a question. I may have to look. So let's say that you have low codimension, high codimension of the target space, and you have complex structure in this target space. Then what do you have these regularity results? I suppose that is your question. And as I mentioned, there is some statement about Levy flat hypersurfaces in that. So that might be able to address your question in that sense. I don't know if you remember the precise. I'll dig it up after this and maybe say a few words about it next time. So they use the same method when it's a Levy flat hypersurface, but in general, there the complex structure is fairly straightforward. But if it's more complicated in the target space, then I don't know what kind of techniques will work. Okay, so we have non-existence, we have so result C is due to Alexander from these A disk. If you're totally real, you can always expect an A disk. And this, we are going to also sketch a proof. And this is going to use something known as the Fredholm alternative. And so I will discuss the details. I will tell you what a Fredholm operator is, and we will sketch this out. This probably won't happen. I mean, it definitely won't happen until the next lecture. So if you want to go back and recall what a Fredholm operator is, this is a good exercise. The final statement I'm not going to state clearly right now, but hopefully I will get to talk about this by the end of this course. So this result was in dimension 2 was due to Fosterich, and then in higher dimensions due to Klobotnik. It's a fairly technical piece of work. So I don't know to what extent I will be able to give you the details, but I want to be able to talk about a linearized version of this problem. And so this is 87, and this is 94. And what they do is, so here detailed statement will come later, But the idea is they give a condition, they give a sufficient condition on an attached disk. So a fully attached disk, okay, not an A disk. So suppose you already have an attached disk. So somehow for some reason, let's say you're on a Lagrangian submanifold, or for some reason you already can see one attached disk. Then there is a condition, and this condition involves some sort of winding numbers. So hopefully I'll be able to tell you what these are. So this condition, they give a condition, so sufficient condition on an attached disk to guarantee a foliation by nearby attached disks. Okay, so just to keep a picture in mind, we always have our S1 cross S1. Should always keep that in mind. And you know that not only do you have, so always there are many disks attached to S1 cross S1. If I attach all the disks, I get the bidisk, right? And so there are lots of disks attached. And in fact, if you have one of these disks, then you actually have a whole foliation by disks close to it. So what I can do is, if my local picture looks something like this, I can compute a certain quantity over here. And if this quantity satisfies the condition, then I am guaranteed the existence of nearby disks. It also tells me, this quantity also tells me how many disks to expect. Like what is the number, what is the dimension of the parameter space. And if the condition is not satisfied, it also tells me that this is the only disk over there, up to reparametrization. So remember, for us, disks are really maps. And so if I reparameterize using an automorphism of the disk, I don't really count that as a new disk. It's just a reparameterization of the same disk. But I'm genuinely interested in new disks. And so this kind of tells me this result, which is actually quite complicated to state and prove. But I'll try to give you, if I have enough time, I'll try to give you a sense of this. And all of these, all of these you'll notice are referred to as non-linear being able to attach these disks. These are referred to as non-linear Riemann-Hilbert problems. So when I talk about this theorem, I will sort of tell you what a linear Riemann-Hilbert problem is. It actually goes back to Riemann's thesis. So he was actually studying problems like this at some linear level, and so we will, and then sort of Hilbert modified that question. So we will kind of sort of become students of history and go back to this and see what the original problem was and why is this a non-linearized version of these very old problems that we have studied. Okay, so sorry, condition here. Yeah, so it is condition. The condition is on the boundary. Okay, so what happens is that you're attaching to a totally real manifold. So you kind of look at how the tangent spaces are kind of rotating. So you have this totally real, at each point of attachment, you have this totally real plane. So think of this in C2. So maybe I'll focus on the C2 work. I'll see depending on the time. This is in C2 and this is in dimension greater than or equal to 2. In C2, you have these totally real planes, and you kind of want to see how they wind. So as you go along this curve, they're going to wind in a certain fashion. The important thing is, when you have a totally real plane, okay, maybe I don't want to say this right now. I will come to it later, but it's really about the winding of those totally real planes. And this gets a little bit more complicated in higher dimensions because you have totally real n planes. So there are several winding numbers to take into account. Okay? So it's really a winding of these planes along the boundary. So it's some kind of an index. So if you know a little bit of symplectic geometry, there's this thing called the Maslov index. It's a little bit like that, but I don't want to throw a lot of words till we actually get there.
I thought I understood this question as what is it foliating?
Oh, sorry. Did I not understand your question? Did you talk about the foliation?
Yeah.
Oh, sorry. Oh, I'm so sorry. Okay. Yeah. Okay. So I thought you meant conditions. So what it is, it is foliate. Okay. Depending on what number comes out of this, it's going to foliate a manifold of higher dimensions. Suppose this is this is a two surface in C2. In general, you have an n surface in Cn. Okay, so when the condition is favorable, the foliation will be, it will foliate something which is a manifold of higher dimension, and the it will foliate a manifold with boundary. The manifold will be of higher dimension, and the boundary of that manifold will sit inside this surface. So, for example, if it looks like this n surface, then you will get discs like this, and these discs will foliate either in n+1, or sometimes if this condition is extremely favorable, they will even foliate a full open set, which will be like 2n. So it will totally depend on what numbers come out of this. And then there are situations where you'll literally get nothing else. You'll only get this disc. Okay, so if the condition is favorable, you will get a foliation of a higher dimensional manifold that these discs will sort of fill in, but the boundaries will always lie in the manifold that you started with. That is the idea. So these are basically giving you a pretty good sense of the hull, the polynomial hull of this object over here. At least it's providing you with this foliation. Yeah, maybe I don't want to say more than that.
So I have one more question.
Yeah.
So the A disc. So how should we think of, like what should we think of when we think of this missing point? Is it a manifold singularity?
So I think this is something that I don't have a very good picture of. In fact, there are examples of A. I mean, the example I will discuss, I couldn't spot an A disc that easily. This is basically where f prime will go up, because the point is that these. So remember that the area of these discs was, you pull back omega naught. Okay, this is the area of the disc. So you pull back omega naught, and this is going to be something in terms of f prime. And these points are basically what are going to prevent these discs from having a finite area. So f prime blows out. F is still bounded, but f prime blows out. Yeah, exactly. So some pinching over there. And okay, so I'll make this comment maybe when we do the example. But yeah, so this example that I'm going to do Alexander's example, and maybe a good exercise is if somebody can find me an A disc in that. So we'll show that there are no attached discs. We will see something which is attached, but I don't think that's an A disc. So if somebody can actually sit and find an A disc on that would be nice. At least it would be. There is a totally real 3-sphere in C3 due to Hahn and Rudin, and they actually produce A discs in there, but they're very complicated. I didn't want to kind of present that paper. I'll put that down as a reference if you're interested in that. Now the key thing is that this guy allows for infinite area, which is where Gromov's proof will break down for totally real manifolds, because Gromov's proof relies on the fact that these discs continue to have finite area. So what Alexander would have to do additionally to prove Gromov's theorem is he would have to show that if the Lagrangian condition holds, then these A discs actually have finite area, and so they actually patch up at P. Another thing I should say is that the maximum principle actually holds for bounded holomorphic functions. So the A discs are in the hull. Even if they're not fully attached, they are also in the polynomial hull. Okay, so from the point of view of hulls, having A discs is also telling us something about the polynomial hull. Okay, so let us now, I think we have enough time to discuss. Actually, let me maybe pause. All the 4 theorems are on the blackboard. So I have A, B, C. So let me do it this way. So regularity, non-existence, that's kind of a relaxed existence theorem. And this statement over here, this is a statement really about stability of some kind. Okay, I have a disk and I want to know whether I have nearby disks. What I will not talk about, what they additionally also do is they also sometimes perturb the manifold itself. So I have a disk attached to my, so there are these very old results. I mean, you have to understand that these were very hard to prove theorems. So people were working with very specific objects. So I talked about S1 cross S1. So let me mention this result over here. This is an old result of Bedford. And sometimes it's very surprising that people study these very specific orientations, but it's still quite interesting. So I just mentioned that S1 cross S1, the hull is B2, and it is completely foliated by attached disks. And so what he did is, he basically did small perturbations. He took C2 small perturbations of S1 cross S1. So you take the two torus, do a small perturbation. So let's call that M. And what he showed is that M hat is a small perturbation of the two disks and has the same foliation structure. So it is also foliated by the same number of, and I say number, I'm really putting a dimension on the parameter space. So he showed that this has exactly the same disk structure as D2. Okay, so these are like stability results. And so he did this for a very specific case. And this is kind of a more general result in that setting. So stability. Okay, that's all. Let's talk about Alexander's torus.
Say that there's a real two torus C2 that has no
Analytic disk. Attached to it.
Oh, okay, yeah, thanks.
So it's not fully continuous up to the theorem B. Okay, so we'll first start with a preliminary object and then we'll construct our set out of that. So let me take S1. So it's going to be a two torus in C2. And what I'm going to do is I'm going to immerse this and get a figure 8. Okay, so this is all sitting inside R2. Oh, sorry, this is sitting inside. Hang on, do I want it in R2? CC. Okay, so let's say that this self-intersection, so they have one self-intersection. Let's say I have P and Q, which both map to, so this map, let me call it psi. So psi of P is equal to psi of Q. And let's say that the self-intersection avoids the origin. Okay? So I have this figure 8 in C. So, and how do I build my torus on top of that? So what I'm going to do is I'm going to take a map. So I'm going to think of this map as a graph. So let rho from S1 to R plus. So I want a positive map on S1 such that at these 2 points, the values are not the same. Okay, so think of it as some sort of graph. So graph over this S1, and I'm assuming that the value of at P is different from the value of Q. And what is this graph going to do? So above each point over here, I'm going to take a circle. And the radius of the circle is going to be determined by the image of this point over there. So what is my capital M? This is not the final example. So let me call it M tilde. This is, you do the following. You take, to write this correctly. So you take psi of lambda. So this is just coming from the figure 8. And then you take W, this is in C2, such that lambda is from the circle. And if I look at the absolute value of W, that is equal to rho of W. I'll draw a picture so that it becomes clear what is happening over here. So let me draw this circle again a little bit differently. Okay, so above this point, if you are coming from P, you have disk of radius rho P. And if you are coming from Q, you have disk of radius rho Q. Okay, so just above this point, there are 2 circles in this set capital M. And then as you go around, you get, above each point, you get a circle of radius rho of that point. Okay, so let me try to draw this picture in some sort of nice way, if I can. happening in C2, so we have lots of space. So we have this 2 torus. So let's take our time with this. So I have this is my M tilde. And I have this 2 torus, and what's happening is just exactly at one place, the torus is sort of going inside itself, at exactly this one. Okay, so again, the way to think about this is that you kind of have some sort of circle fiber, S1 fiber on top of this figure A. And if I take any point over here, if I look at the point above it, I get a circle. And what is the radius of this circle? So this point is psi of some lambda naught. So the radius of this circle is rho of lambda naught. Radius is coming from this nice continuous function that we have chosen. These are sometimes referred to as spin.
It's a cylindrical disk cross something.
It's S1 cross S1. It is S1 cross
It's
S1.
S1 cross an interval and then attached to an analysis, right? Is that the analysis?
There's no solid piece.
No, so yeah, that's fine.
Yeah, so it's not attached to an annulus. It's attached to
The
two
boundary of an
circles.
okay, yeah,
Right?
two disjoint circles.
No, if the boundary was attached to 2 disjoint circles, you wouldn't get a torus. It has to come back and attach to itself. This is the best picture I can draw with my artistic skills. But okay, I mean, I'm okay to just pause and make sure what. I mean, it's really that you're kind of starting with a torus and then like squeezing it through itself and kind of coming back and attaching itself to.
Yeah, so I thought I would draw like Kleinbot analysis, but maybe not.
No, this is all orientable and all. There's no non-orientability. This is a genuine, diffeomorphically, this is a 2 torus.
I'll think more about it.
Yeah, so it's a little hard to maybe visualize. But you kind of think of it in terms of pieces. So really what you're doing is you are giving, I mean, thinking of it above here is maybe more complicated. Really to each point, I'm attaching a circle. I mean, I have a circle in the fiber to each point.
And then the circle.
If you had enough space, so you think of it as a movie. If I had enough space, this would not be sitting inside. The problem is the way I've drawn it, this is sitting inside this. In some sense, it is, because if you look at the fiber, I mean, it is in that copy of C. It is sitting inside there. So, but it's not a Klein bottle. It is a 2 torus. Maybe my picture is actually misleading, but I don't know of any other way of. Sorry? Yeah, it is a 2 torus. So one will have to check that by hand, that you have an orientation. I don't know how to. Yes, you can probably take. You can probably even set up a diffeomorphism from the 2 torus to this one. But we'll have to do it. I mean, I can take this to be a smooth map here, and then. But you will have to, yeah. I mean, when you have a very specific form for it, you can probably choose an orientation. I mean, I have a very good representation of it, so you can probably choose a global orientation on this. Wait, you'll have to write it down by hand. In fact, exercise, check that this is totally real. Yes, I mean it is really, it's literally S1 process. It's literally S1 process one. I mean, I'm telling it's S1 on this base and it's like copies of, right? So it's literally S1 process. There's really, I mean, I'm really giving you a circle on top of each point in S1. So it's not even a very weird embedding of the. No, it's a 2 torus, right? I mean, to each point on S1, I'm giving you a circle, right? So this is one of the S1s, and this is giving you the other S1. So what I'm doing is that I'm taking my right. I think the confusing part is the way we are doing it over here. That's the confusing part. But if you look at this embedding,
But it's picture is fine because it isn't
written like this, it is. So I mean, if I think of this as you kind of map this picture to this, then it's a little bit more clear. This immersion kind of makes it a little bit more
so
confusing.
it is two disjoint discs over that.
It is two disjoint
Over that
circles,
part.
not even discs.
Sorry, disjoint
Yeah,
circles over that
it's
part.
two discs. There's no solid piece. Okay?
Exactly.
So above this point, in this fiber, you in the torus sees, when you look at the torus above this point, you take this fiber which is C. So this is C and this is C. In that fiber, you will get two circles. But this here will give you an embedding of S1 cross S1 into C. If you look at it from this representation, from the point of view of this representation. So let me keep this here so that I can come back to this picture. This is not our final example, by the way, but it's kind of an intermediate step. And why this is not our final example, can anybody see discs attached to this? So just to get your...
We didn't know the circle.
Yeah, so, okay, maybe not this fiber, but take any other fiber. There are lots of analytic discs attached to this torus, right? So this is definitely not our example because any of these fibers, of course, my fibers have gone outside. Maybe the, so this, think of these as larger. Fine. Better picture.
Annulus attached to that point.
Two circles. There is no inside.
Yeah, there is an annulus, so that's a good question. So let me make a remark about this annulus.
But there are also attached discs, right?
There are attached. I mean, we are looking for a genuine attached disc. Okay.
No, I'm saying even the annulus.
Yes.
Is actually two attached discs. If you just want attached.
No, it's not two attached discs.
If you don't care about the interior, like if the boundaries are
Right.
Oh, I see.
There was just the overlap.
right.
Yeah, they're going. Yeah. So I guess the point is that this guy
That's right. The
is
big one and the small one are
attached.
both attached.
Yeah. It's just two disjoint discs. It's not really a problem. Okay, I'll come back to this piece a little bit later. So I guess you can fill this both in, but I don't want to do that right now. It's going to have some relevance later. Okay. Yeah. You're absolutely right. So you have these two discs over there, and that's not a problem. Okay, so now what we want to show is that if I do have a disk attached, I mean, if I take any arbitrary disk attached to this, then it's essentially going to look like one of these. That's what I'm going to show. So let's, wait. To C2 is analytic. Filled up. F is of the form. So it's going to be constant in the first variable, and it's going to be some R times a finite particle. So let's just write it like this, where is some finite. C is in your figure 8. What did I call this figure 8? Let's call it gamma. So C is in this figure 8, and R is sort of the radius of the, so R is some positive one, which will become clear from the proof. Okay, so let's go ahead and prove this. Suppose F1, so what is F1? I take such a disk, so I take a analytic disk which is going to have two components, F1 and F2. I take an analytic disk attached to this object, I project it down. Okay, F1 is my projection onto C. Suppose F1 is not a constant line. Okay. F1 is open, right, is open, and F1 of D is an open set bound by, so because F is an attached disk, if you look at the boundary of F, that has to go and lie in capital M. So when I do the projection, then F1 of the disk has to have boundary in this figure 8 because of the attachment. So F1D is an open set bound by figure 8 gamma. Okay, so but then if it's an open set bound by gamma, by connectedness, it has to be one of these two components over here. So F1 of D is one of the two components bound by gamma, say omega 1. Okay, so I'll just call, let's say it's this component omega 1. Let me call this point Z0 here, the self-intersection point. And so what I have is, so it's one of these. Okay, now I have this, basically I have this proper holomorphic map from the disk to this simply connected domain over here. If this was the ball, if this was the disk itself, then what would that map be? If I have a proper holomorphic map from the disk to itself, what does it have to be?
Finite.
It has to be a finite Gaussian product, right? So this is not quite the disk, but I can always do a Riemann map because I'll get something which is continuous up to the boundary. So I can always do a Riemann map. So up to a Riemann map, F1 is a finite Gaussian product. So up to a Riemann map, F1 is a finite Gaussian product, which tells me something about finite Gaussian products. You know exactly what they do on the boundary, which implies that F1 restricted to the boundary is an open map in the relative topology. Okay, so we want to say something about the boundary because that's where the contradiction is going to come from. Okay, so now it's worth drawing a picture here. So I have a disk, okay? So I have this blue guy. It's going to go and attach itself like this somewhere. Okay, so because the F1 projection is this piece, it's going to remain on one side. This is a disk. Its boundary is going to lie over there. I mean, there could be more parts of this in this piece. And let me call this point eta naught. The point. So I take eta naught in F inverse of Z. Okay, so let eta naught be in F inverse of Z naught. Then an open neighborhood Z naught of eta naught. So if I take a little piece of, because F1 restricted to the boundary, so actually I want to go all the way over here, right? So this is F inverse of eta naught, or F1 inverse of eta naught. How do I do this? So what is happening is that there's going to be an open neighborhood of this point. Let's say I. Open neighborhood of F inverse eta naught in the boundary is going to map to an open neighborhood of Z naught in omega 1 in the boundary of omega 1. So this open neighborhood under this map has to map to an open neighborhood of Z naught. And that open neighborhood has to be in the boundary of omega 1. Okay, this map is taking the disk to omega 1. It's a proper holomorphic map. And from the structure of this proper holomorphic map, we conclude that F1 is an open map on the boundary. So if I take a small enough open neighborhood over here, it's going to map to a small open neighborhood over here. So what is the issue with that? What is the problem? So remember, I have F1, F2, right? So what happens when I approach Z0 from this direction? And what happens when I approach Z0 from this direction? So right, so the point is, so you look at now you look at F2. So suppose you approach Z0 from the plus direction. Let's call this the plus direction and let's call this the minus direction. From plus. Then these are attached disks. When I look at the absolute value of F2, it is going to approach which value? So let's say plus is going like this, P, and minus is going like this, right? So this is plus. So let's say this is the image. So how is this map going? This is psi of P, and now this is psi of Q. Okay, so technically, I guess this is the minus direction, or I'm actually approaching like this. This is the minus direction. So as you approach from the plus direction, F2, absolute F2 is going to approach rho of P. And as you approach from the minus direction, absolute F2 is going to approach rho of P. F2 is the second component. F2 is the second component. So F2 is always in the fiber direction. And because it has to be attached to the torus, it has to be attached to those circles over there, and we know exactly the radii of those circles. So again, the picture, just to be clear over here, how does this immersion work? Just think of it this way. This is psi of T. I go around, and then this becomes psi of Q. So if I'm approaching like this, I'm technically going up here. And if I'm approaching Z0 from here, I'm technically approaching Q from this point over here. That's what's happening. So when I look at the corresponding map over here, then when I go like this, I'm approaching rho of P. And when I go like this, I'm approaching rho of Q. So absolute value of F2 has this jump, but F1, F2 were continuous maps. So this is a contradiction. So that implies that F1 is a constant. So at least the first component is a constant. But that tells you that the disk is in this single fiber. So whatever this disk is, it cannot spread out like this. It has to sit in a single fiber. If that fiber is not above this self-intersection point, then it's sitting, the disk has to be one of these because again, it's a proper holomorphic map, it's attached to the boundary. So it has to go and sit on this disk. So it is a finite Blaschke product in that fiber. And again, if it is in the fiber above this, by connectedness, the boundary of this disk has to go to one of these two boundaries. So again, it will become a finite Blaschke product. It will become one of the two attached disks. Okay, so, and since now the disk is in a single fiber, I'm not going to write this down, but you can argue this is in single fiber. Okay, by conclusion. So at least this proves this part of the claim. You're not done because clearly this object has lots of disks attached to it. But let me pause. You can see these are all one variable arguments. Nothing, there's no heavy machinery that we are using over here. We are going to modify this example. So let me write down the modified example. We're almost done. Write down this expression and see if anybody can see what is happening geometrically. So now, so I'll consider the following map. I'm going to take Z comma W. This is of course well defined as long as W is not equal to 0. Let me call this capital psi, and my M is psi tilde. And I want you to tell me, take this picture in mind, keep this picture in mind. I'm applying this map to this. What am I doing?
Between size and delta.
I actually don't know if I wrote this map correctly. I did. I'm not sure if this is what's, maybe this is correct. Anyway, maybe somebody can tell me what you
You're
think is
basically
happening.
blowing up all the disks except the problematic analysis.
So I think what's happening is that you are inverting
That's right.
along each, you kind of, so you have these attached disks, and if you now invert about each fiber, you kind of get, but I mean, that's not exactly what's happening because you would get the complementary disk. So some sort of, you are doing some sort of blow up, but it's now it's no longer clear. I guess you're doing it above. Yeah.
The only part that stays finite is the intersection points, right?
That's all safe.
That's right.
That's all safe. I mean, everything is safe because W equal to 0 never intersects this torus,
Sure.
right?
But then all those disks are gone.
Yeah, but these disks, so that's the, yeah, it's not clear to me. No, but the impact is happening on the Z coordinates somehow.
Right.
So it's not clear to me. I
So
mean,
so
the
basically,
picture should change here.
But is that
It's all fiber.
It's gonna be fixed once you're looking at it at a disk, right? You just proved that, right? So Z is just gonna be constant. You have a disk going to that.
Yeah, no, but before that also, I mean, what is this really doing to the torus geometrically? I mean, what should we expect from this picture?
The W is fixed, right? Which means fibers go to fibers.
So if I take a fixed fiber,
Right. So all the action.
no, but
in that
that's
fiber-
not, the fibers are Z equal to C. Fibers are not W equal to C.
I see.
Which is how I sort of got, I was thinking they're inverting in the fibers.
No, that's all.
But the fibers are Z equal to C. So maybe I'll not, I mean, maybe I'll ask you to think about what this means geometrically. This is a good, I mean, because it's good to know how you would cook up something like this. So maybe if somebody can give us some insight into what is really happening geometrically. But just to complete, so now coming to Gigi's point, now the question is, so this is my final object. And let me just also mention that psi inverse is really just ZW comma. Okay, so suppose G, you can check, I mean, if you check that this is totally real, then biholomorphisms preserve this condition. So this is also a totally real torus. And let's say that you have an analytic disk attached to M. Then if I look at psi inverse of G, that is going to be of the form G1, G2, comma G2. This is an analytic disk attached to the original guy. I have this disk attached to this new object. I pull it back under psi inverse. I will get a disk attached to the old object, but I know exactly what these disks look like. So I will get that G1, G2 is some constant. And this constant is in the figure 8, and this constant is never equal to 0. Remember that I chose my figure 8 in a way that the origin never lies on the figure 8. So I have this product, which is a constant, so it's never 0. Whereas G2 is supposed to be this finite Blaschke product. So that means G2 can never be 0. Which means G2 has to be a constant as well. And that tells me that I can only have constant disks attached to this object capital M. We pause. I guess my comments here are not quite correct because I was misinterpreting this geometrically, but
Is that called a twisting process?
sorry.
Is it some kind of a twisting process?
I mean, this is usually a blow up. This map is a blow up along. So what are you doing? You have this.
If you just focus
Sorry,
on
W equal to 0. So it's kind of a blow up along this guy over here. So that's the weird. Sorry, W equal to 0 is what? This is W equal to 0. Right? So your torus is sitting. Actually, your torus is going around W equal to 0. This picture is a bit misleading because these circles, they go around the z-axis, right? Because it's absolute W equal to rho lambda. So this torus is entirely going around the z-axis, and now you're kind of blowing up along that axis. So I kind of want to say that you're kind of within each fiber inverting the circle, but I'm not sure if that's.
pull back the torus. What if we just
Pull back
just the usual torus?
this one?
Yeah.
Wait, hang on. So where are you? So you're taking this capital M here?
Yeah.
Okay.
Let's not worry about M yet. Just the usual one without this.
So you're saying take S1 cross S1 on this side.
Then put it back here, just twisting at every coordinate. And then we can bother about this.
So I don't see the, hang on, so let's see, do I see the twist? So you're saying that if I take S1 cross S1 and I pull it back, which means I take the coordinates Z comma W to ZW comma W. So but so what does twisting mean, right? It's not, the twist is not happening in each fiber there. It's a blow up, but it's weird because, right? It's not that it's not like you're applying the same rotation in each fiber. So I mean, this is a good idea. Forget all these weird tori. Just take S1 cross S1 and see what this map is doing, or in the forward, whichever direction you want. You can either start with an S1 cross standard S1 cross S1 and see what this is doing, or you can pull it back. Should have thought about this a little bit more. But yeah, it's really not clear to me what is happening. Anyway, but if somebody has a good picture, that would be helpful. I don't know how to identify a disks. This by Alexander's theorem, there is going to be an A disk attached to this. I cannot identify it. However, I should mention that let's say you have an annulus attached your manifold N. Okay, so what you can do is you can so you have this annulus attached to your manifold. You can cover it with a strip, and then you can take a Riemann map, which will extend to the boundary minus 2 points over here. So if you have other Riemann surfaces fully attached to your manifold, bordered Riemann surfaces which are fully attached to your manifold, you do have bounded holomorphic disks which are sort of attached to yours. So maybe barring a few points on the boundary, you still get bounded holomorphic disks which are nearly attached to your manifold. So a lot of times people just care about those. They don't actually care about fully attached disks or disks attached except at a point, because these will still go and lie in your polynomial hull. These Riemann surfaces with boundaries inside your manifold, they will still go and lie in your hull. So you can still think of them as, almost disks or disks almost attached to your manifold. So even finding these is helpful from the point of view of hulls. And for many very important examples, people have tried to write down all the varieties that are attached to objects like these. Okay, so the two exercises that I have for you is one to sort of get a geometric sense of what this blow up is really doing. And the second one is, can you actually identify an A disk attached to this? Because we know that such a thing exists by Alexander's theorem. I would say this is a fairly straightforward example. It has a very specific representation. So can we actually write down an A disk attached to it by hand? So I want to stop here. What I will do next time is I will talk about Chitka's regularity result. What are the main ideas over there? And if I have time, then I'll start a little bit with how did Alexander construct these A disks. So that's all. Yes, please. I kind of did not think about this long enough. What do you think? Yeah.